Okay, today we're going to do what will very often be covered in the first lecture on any course on polynomial algebra. We're going to do a very fundamental theorem of the subject today. So, begin with, let me just quickly go through some notation that he uses. So, if you have a set contained in B of H in H, right? H, and you have a set contained in B of H. So, I want to be consistent with my notation now, having these script symbols for Hilbert space and just straight symbols for operators, algebras of operators, sets of operators, and so on. Okay. Then we will write, as I said, we will write this symbol will denote arm close subspace spanned by S. This is the norm closure of the linear span of S. And we will also write this sometimes. But for operators, usually the good topology is this is of H. This is of B of H. Spanned by S. So, okay, so for corrections of operators or algebras, the natural topology is not quite the norm topology for us. What we'll be looking at is the strong operator topology or weak operator topology, and we've seen that the closed convex sets are the same in both topologies. Convex sets are SOT closed precisely when the WOT closed. So I can take either the SOT or the WOT closed subspace into the same thing. And we will write, we just write this, sorry, the other way. This will mean all things of the form x psi, where x is in S and psi is in S. And so we write this, then so what is this? This is the smallest closed subspace spanned by vectors of this form, right? So you must see that. So note that this is in. So note that this is the smallest no. If this, I'll just say, if the identity is in S, if the identity operator belongs to S, then clearly this will contain this set S itself, right? I can take x equal to 1. That means this will be some closed subspace which will contain S. So it is the smallest closed subspace containing S, which is invariant for S. No, I can't just say that. And if S is an algebra, algebra is invariant for S. This is if S is a unital, that means containing one subalgebra of B of H. Okay, so let me back up. So I just started the other way. I'm saying, suppose S is a subalgebra containing 1. Then this contains S, as we noticed. And in fact, because S is closed under multiplication, it will be clear that if you apply any operator in S to this, because S times S is contained in S. If it has identity, then S times S is equal to S. So if you act on this subspace by operators in S, you will stay in this subspace. That means the subspace is invariant for all the operators in S. Okay, so therefore it will be invariant for everything in S. It is an invariant subspace for the algebra. Okay, so this is probably a good time to do this little exercise. See, usually if you have a subspace contained in H, then that immediately gives you an orthogonal decomposition of H as M direct sum M pub. So you can think of H as M direct sum M pub. And whatever I said yesterday about operators on direct sums of Hilbert spaces can be written as matrices of operators. Right? I did the general version last time, right? Not just things in H. Yes, last time was I assuming that all the HIs were different, or was I taking HI equal to H? Different case. So I said if you take B of HI, direct sum HI can be identified with all matrices indexed by the index set of the i's where the ij entry is everything in B of Hj, Hi. So this is something that we saw last time, right? So if we have any operator on B of H, in this decomposition, you can identify it with the matrix Xij. Right? Actually, X11, X12, X21, X22, where X11 will be an operator from where to where? From M to M. And X12 will be from M up to M and so on, right? Okay. So now I want you to observe a simple lemma that in that notation, I want to say that the following are equivalent. One, X maps M into M. I want to know what it means for a subspace-free invariant for one operator. So how does this act on things in M? Things in M look like column vectors whose second coordinate is 0. And if you apply this to such a thing, you will get X11 psi, X21 psi.
X21 is 0. X21 is 0.
No, I haven't said X21 is 0. So I want to say this is equivalent to saying that X21 is 0. So this is first problem. Second part, if P is the projection onto M, the orthogonal projection onto M, then P will have a matrix in that decomposition, right? M direction of M per. So then what is that matrix corresponding to P? Huh?
X11 0 1 and all other are 0.
And okay, then let other people think and talk. This is just it kills M pub and sends its identity on M. Right? So this is what the projection on M looks like. Okay. And so for A, I want to say, so after giving this, so going back to A, I'll say this third condition is the same as saying, what can you say about, how can you capture X21 if you know this? So I want to say 1 minus P XP is 0. See, in general, I want you to observe the following thing. If you take a diagonal matrix, lambda AI, and if you multiply it by a matrix Xij, let me do it on both sides. So see the difference in left side and right side multiplication. Suppose you take two diagonal matrices and multiply by a square matrix in the middle. What will the ij entry of the product be? Sit down, multiply it and tell me. Levi, you tell me. Sit down, multiply it. AI.
XIK summation.
You please do it. Take a 3 by 3 example and multiply it and see what you get. Don't talk, you do it. And tell me what you get. What will you get if you take AB, PQRS, CD? What will the answer be? End with that. It's just no summation, nothing. You just so diagonal matrix. We multiply only one term with somewhere every time. So this is what the matrix is going to be. So, for example, see P is this and 1 minus P is going to be 0, 0, 0, 1. Right? So, if you want to lay hands on any of the x11, x12, x21, x22, you will be able to write this as. So, for example, to say that x2, what is x11 in terms of P and x? If I know that x is the matrix xij, how can I lay hands on x11 using P and x? You must multiply this by some diagonal, pre and post multiplied by diagonal matrix, which leaves only the 1 1 entry and kills everything else. So what should you do? Px pair. So notice that Pxp is just x1100. 1 minus. So I'll write P pub rather than 1 minus P to be the same thing. P pub xp will be, this is the one in the second spot. This will be x21. PXP perp will be 0, 0, x12 and P perp XP perp will be for this reason PXP will often be referred to as a corner of X. You take an operator X and if you pre and post multiply it by a projection, you will call that operator the corner of that operator corresponding to that projection P. Namely, what does it do? It takes something in the subspace M. What does PXP do? See, PXP in general is the operator on this is okay. This is xi. If you take, then there is going to be 0 xi is in kernel P. There is range P perp. And if xi is in range P, what will you do? First you will do, what is P xi? P xi is xi. So there will be just P x xi. That is, you apply x on xi, but see, in general, if you have a subspace and if you have an operator acting on the big space, from that you want to manufacture an operator on the subspace. What you can do is take a vector in the subspace, operate on it by this operator x, but then that is in the big space. That will have a component in the subspace and in the complement. So if you want to get an operator on M, then you must kill off the remaining part. So PXP does exactly this. So in fact, one calls this, one calls X11. Okay, so let me go back to this and introduce some terminology. See, we have seen that in general, X, if you take any X, it may not leave M invariant. It may not leave M invariant means that X21 may not be 0. Right? So, in order for you from an X in B of H to get something in B of M, so one calls PXP, one calls the compression of X to M. That is in matrix form, it is just that X11. Now, it's only when M is invariant under P, there is a compression of X, that you can talk about the restriction of X to M. The restriction of X to M will be a map from M to M only when M is invariant. Only then you can talk about So anyway, so we've seen that being invariant. So another little. I'll show a corollary of this previous exercise. If I'll say S in general, if we take a collection of operators acting on a collection of vectors, then to say that this is contained in S if and only if. See, what does this mean? This means that for every x in S, it must be invariant. That is, that this third condition, this condition must hold. This or equality, this can be written as Pxp is xp. Right? So this is equivalent to saying that Pxp equals xp for all x in S and P equals Pm. Or in matrix language, you put all of them as matrices, all of them will have the 1, 2 entry as 0.
Small s is n.
Huh?
Small s is n.
Sorry,
Small s.
sorry, M equals the span closure. Okay, and if S equals S star, okay, this also I should have defined. So if I have a collection of operators, what I mean by S star is just the collection of adjoints of the operators to start with. That is, this means that the set collection S of operators is closed when taking adjoints. If S equals S star, what does this say? This says that for every x, the 2, 1 entry is 0. But the operator is closed under adjoints. That means x star should also have the 2, 1 entry 0. But what is the 2, 1 entry of x star? It is the adjoint of the 1, 2 entry. So the 1, 2 entry should also be 0. Then S is equals contained in S if and only if xp equals px for all x and S. And you just look at the matrix. xp equals px. What matrix will satisfy xp equal to px? You take a matrix and you want to say xp, what is xp? You've already done you know how to multiply matrices by diagonal matrices. xp will just retain the first column and put 0 in the second column. px will retain the first row and kill the second row. To say that xp equals px means that 1, 2 entry and 2, 1 entry should be 0. That's exactly what I was saying before. That is that every element of S must commute with P. That is what this says. Okay. So do I need to say anything more about this? Yeah. Okay. So now let me introduce some notation. This has made this notation natural at this stage. For S contained in B of H, we write S prime equal to the so-called commutant of S. Algebras usually use the word centralizer, but in operator theory it can become conventional to call it commutant. What is this? This is all those things which commute with everything in S. And okay, so I want to make a little point here. Notice that I have written x prime in B of H here. I could have written y in B of H so that yx equal to xy for all x. This as well. But this notation is deliberate because if you consistently write x prime for things in something prime and the unprimed for things in S, then without even thinking you know that you have an x prime and you have a y, then they will commute. Right? So it makes algebra much simpler. In fact, my advisor Hermos used to say that good notation helps you to think. Your mathematics thinking becomes better, your exposition becomes better if you use notation which helps thinking, which helps keep concepts in mind. So I would advise you to follow this style of mine of writing primes for things in commutants, even for elements of things in commutants. Okay, so a little lemma or proposition. Let S contained in B of H. S, by this I mean S is just a set of operators. Then what all can you say about S prime? Somebody other than these two. You tell me the maximum you can about S prime. What kind of structure does it have? S prime is, what do you say, the subspace. That is closed under linear combination. Huh? It is a subalgebra. It is closed under product. We have two things which commute with everything in S. Then product, one by one you can pass them over the thing, and so the products also will commute. So it is a subalgebra. Now you only gave me the algebraic features. What about the topological features? Closed in what topology?
Non-close.
You can do better than that. Unital. It is unital subalgebra. It contains the identity operator, right? Identity comes with everything. By norm closed, what you are saying is that if xn prime converges to x prime and xn prime and s prime, then x prime must also be in s prime. Do you need norm convergence for that?
WT also. WOT will also work.
Or SOT, whatever. Because the subspace is convex, so it doesn't matter whether you say WOT or SOT. Why is it SOT closed? If xn prime converges to x prime SOT, you want to say that x prime is also in S prime. So you take any x in S and try it against your x prime. X prime x of xi will be, by definition, the limit of xn prime x of xi, which you can then commute, when then you can see that x prime must be in S prime. So all this you get for free. The commutant of anything is automatically a W2 weak operator closed unital subalgebra of B of H. Okay. And if S equals S star, then S prime is also S prime star. S prime is also closed under adjoints, I want to say. You take an x prime and S prime, I want to say its adjoint is in S. If I know x prime is in S prime, it commutes with any x in S. You look at that equation and you take the adjoints. And you will find that x prime star must also commute with everything in, because adjoints of things in S will exhaust everything in S. So the commutant of a star closed set is star closed. So if therefore S equals to star implies S prime is a one-dimensional algebra. One-dimensional algebra I defined for you as a unital WOT, closed star subalgebra. And all the structures this has been shown to be satisfied by such set. So you take any star closed collection of operators, its commutant is automatically a phenomenal algebra. Okay. Okay. Another silly little proposition. I want to say that S prime okay. I'll start with something. If you have S contained in T, you have two collections of operators. Then what is the relation between the commutands?
S prime content T.
So the inclusion will be reversed. To be in T prime, you have to commute with more things. You have to commute with everything in T and hence also with everything in S. And so it is your content in S prime. Okay. And then I want to conclude from this that S prime equals S triple prime, by which I'm writing rather than, by this I mean you take S prime, take its prime, take its prime. So I'm sparing myself writing many brackets. It is the third commutant of S. I want to say there is the same with S prime. Why is that? Because the one already implies that wait. See, no. You apply.
S double subset of the S.
Okay, let me write that first. S subset of S double dash. To be in S double dash means you must commute with everything in S prime. But by definition, everything in S commutes with everything in S prime. So, by putting these two things together, I want to conclude that S prime is equal to S triple prime. Because if I apply 1 to this relation, I have S prime contains S triple prime. On the other hand, S triple prime is the double prime of S prime. So it will contain S prime. By what this is said. So 1 and 2 imply 3. Right? So always S prime equals S triple prime. So here's the situation. If you take an S and you keep taking commutants, you keep on taking commutants. All the odd guys are the same. Right, this follows by applying the previous thing to S prime. S prime equal to S triple prime. So if you take commutants in this equation, you have S double prime equal to S 4 primes. And so on, right? So if you look at this whole collection of equations, there is only one place where you don't have an equation, you only have an inclusion. right? Which is this S contained in S double prime. And of course that need not be equal because S need not be a subspace, it need not be a subalgebra, it need not be a one-Neumann algebra. Any prime is a one-Neumann algebra you've seen. This S is already any old set. So the only fellows who can hope to be S double prime are one-Neumann algebras. And we'll see that that is indeed the case, and that is a characterization of one-Neumann algebras. Okay, so I want to prove the one-Neumann. Density theorem. Let A be a contained in B of H be a star algebra. Let me say be a unit of star algebra. Actually, we don't need unital, something less than that is enough. So let me digress with that little something else. So okay, let me go through the proof and then I'll tell you why the other thing is enough. Then A is SOT dense in A double prime. Because if you have a star algebra, then it is SOT dense in its double commutand. So if A is already SOT closed, then A must be equal to A double prime. So if A is a one-Neumann algebra, then A must be equal to A double prime. Now, okay, let's see how the proof goes. So now we have to review what our understanding of the strong operator topology is. The strong operator topology is defined by a bunch of seminorms, and hence you have a topology where there is a bunch of, there's a subbase of open states which generates the topology, which comes from those seminorms. And so you must take a finite intersection of those subbasic sets to get a basic open set. So what is a subbasic open set? Where one of those seminorms is small. Right? That means you take a vector xi in H. So you want a subbasic open neighborhood. Okay, so what do we need to prove? So let A double prime in A double prime. Now I want to take a subbasic open neighborhood only. So what does the subbasic open neighborhood of A double prime look like? You take one vector psi and look at the place with respect to the seminorm p psi. You look at the p psi epsilon ball around A double prime. There is all those x such that norm of xi minus A double prime psi less than epsilon. So for some epsilon and for some xi in H, this will be a subbasic neighborhood of A double prime. So to get a basic open neighborhood, you must intersect finitely many of these things. That means you must take something like intersection I equals 1 to n xi I minus A double prime xi I less than, you can write epsilon I, but actually you can write 1 epsilon, that's enough. You can take the smallest of those, and that will be also a basic open neighborhood contained in the other basic open neighborhood. So things like this form a basic open neighborhood of A double prime. So we want to show that we want to say that subbasic open neighborhood contains something in A. Right? Is this clear? This is what a basic open neighborhood of A double prime looks like, and you want to show that every basic open neighborhood of A double prime contains things in A. So this is what we'll have to do. So rather than, sorry?
I was asking, this is the subbasic open set for SOT.
Yeah. Yeah, in the SOD. Strong operator topology is norm convergence at each xi. Okay. So we will make things easy for ourselves by first considering the case, simple case. I assume that n equals 1. Let's first do that case. At least in the subbasic open neighborhood, let's find something. So what does that mean? That means we are given one psi, we want A in A, such that norm A psi minus A double prime psi less than epsilon. This is for any epsilon. For each epsilon, we want this. Or equivalently, i.e., we want an in A such that norm A, such that an psi minus A psi A double prime psi converges to 0. This is what we need to do. Okay, so von Neumann says, you consider the following thing. Another bit of general gyan let me give. When you see mathematics and proofs written by great mathematicians, you will see that things are really elementary when viewed right. Things aren't artificial. And in a lot of universities today, people write PhD theses and they take some unknown theorem from somewhere whom nobody ever uses and generalizes that to some other constant thing. You have something true in some kind of normal topological space, then you introduce something called a sigma normal topological space, and you prove that same theorem about normal spaces in sigma normal spaces. Or which nobody will probably ever use in ever in the future. Whereas if you see something like this, and these are things which arise completely naturally, and the proof is completely natural, and it is very beautiful in its simplicity. If you look at the proofs, you see how he tackles this problem. The proof is so simple when viewed right. So it says, okay, you do the following thing. You look at, so what do you want to show? So you want to prove that A double prime psi belongs to what we call A psi. Right? This collection of operators acting on just this one vector, the singleton set. I want to say the closed subspace spanned by A psi must contain A double prime psi. This is what we want to say. Okay. So what I will say, let's call this subspace M for the moment. And let's let P equal to projection onto M. Now A is an unital algebra. Right? What we saw last time was that if A is a unital algebra, then any subspace like this is going to be invariant for A. Right? So this is invariant for A. M is A invariant. So what does that mean? We wrote another thing before. If we have a star-closed collection of operators like this A, to say that some subspace is invariant under this algebra, star algebra, is the same as saying that this star algebra must commute with the projection onto the subspace. Right? That was one of the conditions we got. We got that P must commute with everything in this star-closed algebra. Therefore, P is in M A prime. You have an algebra which is a subspace which is invariant under A. Is the same as saying that the projection onto the subspace is in the commutant domain. So this is what it says. But if P is in A prime, but then P commutes with, I'll write this symbol for commuting, with A double prime. A double prime was chosen from the double commutant, which is all those fellows which commuted with everybody in A commutant. In particular, it must commute with this P. Now, if A double prime commuted with P, then in that matrix form, A double prime must be in diagonal type, must have 0 on the off diagonal blocks. In particular, A double prime must leave M invariant. It leaves not only M invariant, it leaves M perp also invariant. Therefore, A double prime M contained in M. But I am interested in the in the element A double prime, in the vector A double prime psi.
Psi belongs to A.
So I want to say this belongs to this. Xi belongs to M. Why does Xi belong to M? Xi belongs to M because A contains 1. A contains 1, so Xi belongs to M. But if Xi belongs to M, then we proved what we wanted to prove. A double prime psi is indeed in the closure of this subspace. You must really go back and think about this, digest this proof, because its simplicity hides a lot of what is going on. And to get a feeling for what is going on, you will really keep staring at the proof to see what it says. Okay, so we have proved the theorem in the we proved that subbasic open sets intersect A. But now we want to go to basic open sets. So we'll go to N, and this is another brilliant trick of von Neumann's. Case 2. N arbitrary. Okay. Then, to hear the brilliant idea of the man, he says, right, consider the set defined by So I look at A in A and look at n by n matrices which have A everywhere on the diagonal and 0 everywhere else. Okay. So let us call this object, we'll give it a name, let us call this A to the n. For an A in A, we'll write A upper n to denote this operator. I say this operator. Where is this an operator? I've written a matrix. So this is an operator on what space? Huh?
Direct sum of direct sum
பலமா சொல்லுங்க.
Directions of which?
Direction of n copy the weights, right? It is the operator which sends I1, I2, N to A1, A2, A n. Right? So in this we made this identification of B of h to the n with Mn of h. Mn of B of h. So now I ask you, what is, now that you have carefully spent some time training you to become masters in multiplying by diagonal matrices from the left or from the right, you should now be able to tell me what is An prime. That is, I look at a matrix Xij in so what is it? This is all those Xij matrices, where each of them is from B of H, such that if I multiply this on the left by A to the n, that will be the same as multiplying this on the right by A to the n. So what is multiplying it on the left by A to the n, what will it give me? The matrix with any entry? Axij. So what should I write? So you tell me, what is this? What is the equation that I have? When will an Xij satisfy that condition?
Axij equal to Xij.
Axij equal to Xij A for all A in A. Right? Which is really, I will write that means where are the Xij's? Xij's all come from A prime. So this I can identify with Mn of A prime. Okay. So An double, now I want to look at what An double prime is. This will be all those matrices Xij such that Xij must commute with any A prime Ij. Xij must commute with any A prime Ij for all A prime Ij in A prime. Right? When will, such a matrix commute with all such matrices. This, so I claim that the answer is going to be if you take something of the form A double prime n, then that will commute with any A prime ij. I am claiming that those are the only ones who will commute with all of these. To see this, I first so the exercise by saying do an exercise. You use A prime ij equal to delta I, no. Yeah, I should say Eij. That is the matrix with just an identity in the Ij place. Eij means identity operator. Identity in the Ij place, 0 elsewhere. And then to see that it commutes with, to say that Xij commutes with any such E matrix, all E matrices will force the Xij to be diagonal and to have all diagonal entries equal. So I'm saying that in fact I'm saying use Mn of C times identity commutant equal to B of H n. The only things which will commute with all n by n matrices which are scalar multiples of identity in every spot, precisely when it is a matrix of this form. All diagonal entities are the same operator, all off diagonal entities are 0. Now if you know this fact and then you also wanted to commute with all A prime ij's, then it must commute with everything of the form A prime on the diagonal. It must commute with all A prime n's. That will mean that if an x upper n commutes with A prime upper n, then x must be in A double prime. So this says that A n double prime is equal to A double prime n. Time very good. I can finish this. So let us go to what we have to prove. What did we have to prove? We had to take the subbasic open neighborhood. We want A double prime and A double prime such that norm of A double prime xi minus A xi is less than epsilon for all A. Where A was something in A. We started with something in A. So this is what we want to prove. So I say, you apply the n equals 1 case to this, by n equals 1 case. Applied to an. Look at a to the n. Now this is as much a unital star algebra as A was. This is a unital star algebra and B of Hn. So by our n equals 1 case, I take one vector in that Hilbert space H to the n. Which vector do I take? I look at this vector xi1, xn. So what does this case say? There exists somebody in its double comitant which is close to it at this one vector. What is its double comitant? An double comitant is A double comitant upper n. That means you must have something of the form A double prime upper n in this, which is equal to A double prime upper n. So the n equals 1 case, there exists such an operator such that norm of is an epsilon. Sorry. We want an A in it. You're right. Yeah. I want an A in A so that is close to A double prime. Where this, so we take something in the double comitant of this A upper n. There is, so okay, you're absolutely right. To an double prime, I should say. What does any case n equals 1 say? You take any star algebra A and you take any vector in A double prime, you can approximate that at any one vector by something in A as close as you want. So I take any, I should have said there exists this an in an. See, I started with A double prime n in that. Is it clear? I'm getting tongue-tied. Is it clear what I'm trying to say? No, not clear. What did we prove with the n equals 1 case? We're given a star algebra A and you take any A double prime and A double prime and any vector xi in H, then you want to say there and an epsilon. You want to say there exists an A in A, so then norm A xi minus A double prime xi less than epsilon. So now I am saying, let us start with the star algebra A_n, and then look at something in its double commutator, which is equal to A double prime n. So start with something there means you start with any A double prime n. So this will say, and you take any such thing and you take a vector, namely this xi, and any epsilon, then there exists an an, there exists an an and an, which is the same as saying there exists an A in A, such that this inequality holds. And this certainly implies that for each of them, this means exactly that. So what does this say? This is summation A double prime xi minus A xi squared epsilon squared. That is what that says. So in particular, each term must be smaller than epsilon. And so we have proved von Neumann density theorem. After all these years, now it is what some 75 years since he wrote down the proof of this theorem. You'll never see any other proof of this double commutator theorem. This density theorem. So the corollary that we want is the double commutator. Let A M contain B of H. Be a unital star algebra. And the following are equal. One, M is SOD closed. Which we know is the same as saying M is WOT closed. Which is the same as saying And what is amazing about this theorem is that here is a condition which is purely algebraic. In B of H, you take some connection, a star algebra M, and its commutant is a purely algebraic thing. So W commutant is also a purely algebraic object. So this 3 is a purely algebraic requirement on M, whereas 1 and 2 are these topological requirements on M. And it says that this structure, there's something fantastic about this structure that says that having this algebraic property is equivalent to having this topological property. And in fact, we will soon see that in fact also later I'll show you this fact that M is sigma weakly closed. Okay, I think we've good place to stop after proving a good theorem. 2 pages. Okay.